right, so radioactivity. You hear a lot about radioactivity. What is it? Well, it's the result of an unstable nucleus trying to stabilize itself. There's a number of ways in which we can predict radioactivity as to whether a nucleus is stable or unstable, and not only predict that, but we can predict what particle is going to be emitted from that reaction. Now on page 900, you might want to turn to that before we go much farther and follow along on me. I'm going to do a rough version of what the chart shows on there. It has something called the band of stability. Which I think is an awful name for a rock band, because who wants a stable rock band? They probably don't make very good music, but regardless. The stability band there talks about whether you can predict a nucleus is going to go through a radioactive decay or not. It's just not a real good way of showing it, but the idea is wonderful. So basically, this is what's going on here. You have your X and Y axis here. The X axis here is the letter Z, which represents the number of protons. And the Y-axis is M, which represents, as you can probably tell, the number of neutrons. The Z part is actually for the German word for number, which begins with a Z. I don't remember. I've had this thrown at me once and I don't remember. But regardless. And you get this kind of interesting little curve. Now, I'm just going to draw basically the middle of the curve that you see there, the golden area, the band of stability. But it looks something like this. It starts off as a straight line and then it goes off right around where chlorine is, element number 17. That's when things start to go away from a 1-to-1 ratio. And then it goes all the way up over here, and then you get to the unstable part where we start looking at it, because once you get to element 89, then all the elements are unstable, and we're done looking at the band of stability in terms of what this represents. Now, what a slope represents is the ratio of the y-axis to the x-axis. You remember that from algebra. So since slope is equal to delta y over delta x, in this particular case, the slope is equal to n over z. So this is the ratio of neutrons to protons. And like I said, it's a 1-to-1 ratio here, and then it starts going up higher than 1-to-1. As you see, the slope gets bigger and bigger as you go up there. Now, if you have a nucleus that lies to the left part of this band of stability, say like right here, you're looking at a beta decay. And in this area right here, this is going to be what we call a positron decay. Now it's also known as electron capture, and I'm not going to deal with that. I'm just going to look at decay reactions. If you get into this in college, then they'll talk about electron capture. But these are the two areas that I'm going to deal with as far as decay reaction. A decay reaction simply means you're going to start off the nucleus, it's going to kick something out of the nucleus, and it's going to create two new nuclei. Okay? And there's three ways. Well, let's take a look. There's an example I use for this, and that's technetium. So let's take a look at that. Technetium 99, which we can write this way. Remember, there's two ways to describe isotopes in nuclear chemistry. For the sake of argument, for writing equations, I'm going to use this, and when writing it on the script, I'm going to put this because it's a lot easier, because it's kind of an awkward situation using this on there with the fonts involved. So what we want to know is if this is unstable or stable, and if it's unstable, what particle is going to be kicked out of the nucleus. Now, there are three systems that we can use. When it comes to the band of stability, the first system that we're going to use in this particular case deals with what we call the average atomic mass. Now, you need to get your old periodic charts for Chem 2 or look at one online or something and find the average atomic mass of technetium. It turns out the average atomic mass of technetium, rounded off to the nearest whole number, is 98. And since this is element number 43, that means then that you have 43 protons and you have 55 neutrons. Technetium 99, however, has 43 protons and 56 neutrons. So when we take a look at this band of stability here, the ratio of 55 to 43, of course, is less than this right here, 56 to 43, or since we probably should put it in comparison to what it says in the periodic chart for the average atomic mass, technetium 99 is going to be greater than technetium 98. So the rate is slightly higher, the comparison of neutrons to protons. So if we take a look at this right here, if we say that 99 is somewhere, or I'm sorry, 43 is somewhere around here, if this is right on the band of stability, this would be 98, or if you want to look at it the other way, 55 to 43. But since 56 to 43 is the other one, which is 99 right here, that's your ratio of neutrons to protons, then this is to the left side of the beta decay, meaning then that we would expect to have a beta decay for this particular reaction. So if I were to write the reaction showing the beta decay of this, I'm going to start with what I'm giving here, the technetium 99. And it would be a good idea to use the periodic chart to get the whole thing written, mass on top, atomic number on bottom. This is going to kick out, and like I said, a beta particle, which is 0, -1. And then we have to make sure that the numbers on top and bottom are going to stay the same. Now, I don't know if it's technetium or not, but I know, well, actually I do know because that's -1 there. If that had been a 0, this is not going to change over here. But these two have to add up to 43 over here, so I know that this is going to be 44 right here. These two here have to add up to 99, so I'm going to put 99 right there. And it turns out that element number 99, or 44 rather, is ruthenium. So there's your beta decay reaction. Not the most challenging stuff we've done, but you do have to get the information off the periodic chart and be able to transfer that idea over to the band of stability, the worst rock band in the history of mankind. All right, so that's one of three ways that we can determine if a substance is radioactive or not. The other two ways, I love this one.